Thanks. So for the last couple of years, I've been writing a linker in Rust called Wild, but I've given some talks about that before. So today I'm going to talk about something linker adjacent. So I'm going to talk about how an executable gets created. At a high level, when you run cargo build, the cargo will run multiple Rust C processes, one for each crate that you're building. The last Rust C invocation, which is usually building an executable, assuming it is building an executable, will run the C compiler, which in turn runs the linker. And the linker is what writes the executable out to disk. You might be wondering why the Rust compiler doesn't invoke the linker directly. And this is because the C compiler is what knows how to link against libc. The Rust compiler doesn't. And we need to link against libc if we want to do useful things like allocate memory. Executables are composed of multiple loadable segments. So the kernel, when it loads your executable, will load these segments into memory. The segments can have different access permissions. So some will be read-only, some will be writable, and some will be executable. Importantly, the executable segment is not writable. So in the bad old days, we used to just load everything into memory and it was all writable, it was all executable. And that meant that if there was a buffer overrun or something like that, that buffer overrun could write code that could later be executed. So by separating the permissions, we make it harder for attackers to exploit things like buffer overruns. The Rust compiler, when it runs, by default, will generate a dynamically linked executable. Dynamically linked executables can depend on shared objects. This is why we dynamically link them. So a shared object is a separate file on disk that is loaded into memory alongside your executable and can contain a library of code, so functions that you can use, data that you can use. Dynamically linked executables also have what's called an interpreter. So this is a bit different to interpreters you might be familiar with from Python. In this case, the interpreter is just responsible for initializing your application before it runs. So the first thing that runs after your binary starts is the interpreter. That does a bit of initialization work, and then it hands over control to the rest of your code. On Linux, we can also generate entirely statically linked binaries. So in this case, everything, the binary is self-contained. So any C library will be built into the executable. This means there's no interpreter and no shared objects. This is less of an option on other platforms like Windows and Mac, because on those platforms, there's no stable way for your program to talk to the kernel other than through a dynamically linked libc. Well, I guess you could statically link it, but it wouldn't be very portable because the interfaces to the kernel can change. Another way in which binaries differ is whether they are position independent or not. So a binary can specify a load address, and the kernel will then load the binary at that address. That means that the binary can know exactly where everything will be in memory. So at link time, it can know exactly where a particular function will be and what its absolute address will be. However, binaries can also be position independent. This means that when they're loaded, the kernel will load the binary at a random address in memory. This is another security hardening technique. So if an attacker manages to find a vulnerability in your code, then it's harder for them to exploit that if they don't know what address everything is going to be at. They've got to figure that out before they can do stuff. However, this does incur some overhead on startup. So because the binary can be at any location, any parts of your program that need absolute addresses need to be fixed up before it can run. And depending on how many of these you have, it can incur a bit of startup cost. So this is done by dynamic relocations. So dynamic relocations are instructions it's a table of instructions in the binary that are processed by the runtime, either by the interpreter or by part of the runtime that's baked into the executable. And they go through and figure out addresses for things and write addresses into particular locations in your program's address space. There's a few different types of dynamic relocations you might encounter. So there can be dynamic relocations that request the address of a symbol. So this is useful if you've got a symbol defined in some library that you're linked against, like in libc. So you don't know the address of that until runtime because you don't know where libc is going to be placed in memory. There can also be relative relocations. So these are useful for where you've got a position-independent binary and you've got a symbol that is in your binary, and you want to know the absolute address of that symbol, then a relative with addend relocation will take the base load address of your binary and add some fixed offset, and then write that to the address of the relocation. There's also several relocation types related to thread local storage. So it's kind of an ongoing theme with writing linkers, is that thread local storage is really complicated, and there's just so much to it. There are heaps and heaps of different relocation types, and I don't know how many times I've encountered bugs due to not getting thread local storage quite right. Another interesting type of relocation are called ifuncs. So these are a GNU extension, and they allow you to have multiple versions of a function, and at program startup time, select which version to use. So the way these work is you have an ifunc resolver, which is a function. It gets called at startup, and it checks to see what features are supported by the current CPU, and then will return a pointer to the function that it's selected. So you can have one version of the function that is optimized for the latest CPU features, and then some fallback versions of the function that are used if the CPU you're running on doesn't support those features. It was also used by the XZ supply chain attack, since it's a mechanism that runs fairly early on in initialization. Another GNU extension is relro. So in order to apply a relocation, the memory address at which the relocation is applied needs to be writable. But a lot of the things that we're applying relocations to are things like the global offset table, which is an area of memory that contains a whole bunch of pointers to things. And we don't really need that to be writable after the program has started up, after the relocations have been applied. And so relro is a way of putting something in the binary to tell the loader that once relocations have been applied, we can remap those parts of memory as read-only. And that means that any exploits, any vulnerabilities that get hit afterwards can't overwrite those things like the global offset table, which makes for improved security. When the Rust compiler runs, each of your dependencies will get compiled to an rlib. An rlib is an archive file with a .rlib extension. Archive files are a container format, so a bit like a zip file, but without compression. And importantly, the linker knows how to read archive files, so that's why we use them. Inside that rlib, there's crate metadata, which is everything that the Rust compiler needs in order to be able to build crates that depend on your crate. In addition, there's a whole bunch of object files, one for each code gen unit. So when the Rust compiler compiles your crate, it will split it up. Generally, it will split it up into multiple code gen units. This allows it to run LLVM in parallel, which makes better use of the multiple threads that you probably got on your computer. And each of those code gen units gets written to a separate object file inside the rlib. One of the most important things inside object files is symbols. So symbols are the way that we match up a reference to a function and the definition of the function, which are often in different object files. Symbol names written by the Rust compiler are generally mangled. So this is an example of a mangled symbol name. And it's a little bit unreadable, but there's a few important things here. So one is that Rust lets you depend on multiple versions of the same crate. And though the symbol names from those multiple versions of the same crate need to not conflict. And so the Rust compiler adds stuff in here to ensure that those symbol names are unique and don't mess with each other. If we look closely, we can also see that there are some bits in this symbol name that are readable. So core format write is in there. And indeed, if we pipe this symbol name into the program rustfilter, it will print out the unmangled name of that symbol. Symbols can also be versioned. So the Rust compiler doesn't make use of symbol versioning. However, a lot of libraries that we might link against, say libc, do make extensive use of symbol versioning. So we can see here there's two different versions of the symbol memcopy. If we were to build our program on a version of Linux that had an older version of glibc, suppose we built it on one that had one prior to 2.14, at that point the default version would have been glibc 2.2.5, and we would have, the linker would bind to that version. So if we then run on a later version, it will still use that older version of that function. So the double at in the second line means that that's the default version. So when we build on with these ones, it will use that later version. but it's the version that's present at link time that is used. So this is why often when people are doing release builds, they will do the release build on an older version of Linux, because it means you bind it to an older version of the function, which you can still then run on newer versions of glibc, because those older versions are still available. If conversely you build on a newer version, you often can't run your binary on the older versions of glibc. Symbols have what are called binding. So this relates to how the symbol works across object files. So there's 3 different bindings. Global binding means that the symbol can only be defined in one object file. If it's defined in more than one, then that will be a link error. It can also be referenced by other object files. So you can have one object file that defines the symbol globally, and other object files can reference that symbol. Local binding, however, means that it's local to the object file, so it can't be accessed from other objects. That means if you've got it in one codegen unit, it can't be accessed from a different codegen unit. It also means that the symbol name is not important, so you can have the same symbols with the same name in multiple object files, and that was perfectly fine. Weak binding is like global, but you can have multiple symbols with the same name, and the linker will pick the first definition. You can also have one with global binding, and it will use that in preference to all of the weak symbols. Or you can have no definitions at all, in which case your code needs to be able to handle the symbol resolving to null. So that's for regular object files. For shared objects, we have symbol visibility, which is kind of a similar idea, but a bit different. So default visibility means that the symbol can be defined in one shared object and referenced in another one. It can also be defined in multiple shared objects, and whichever shared object is earlier in the load order will get priority, and that's the version of the symbol that will be used. So this means that any references to those default visibility symbols need to be dynamic. So you can't assume, even if your shared object defines a symbol, you can't assume that that definition of the symbol will be the one that will be used, because there could be an earlier shared object that defines that same symbol. And that means you've got to run a startup cost in order to access that symbol. This is important because the Rust compiler, if you're building, say, a dilib, all symbols will by default end up as default visibility. And so you do incur some runtime startup cost there if you've got a large dilib. Protected visibility overcomes this, so it says that you can only define the symbol once. So whatever shared object defines it, that's the only shared object that's allowed to define it. And that means that you're now free to assume that that symbol won't be defined elsewhere, and so you can make direct references to it, and you don't need dynamic relocations. Hidden visibility means that the symbol cannot be accessed by other shared objects. So it's effectively like local, but for shared objects. So relocations are instructions that are emitted by the compiler for the linker. They're grouped by section. So each section will have a table of relocations for that section. You can kind of think of a section as a bit like a template, and the relocations are placeholders that the linker needs to fill in. So as the linker copies the section into the output file, it fills in those placeholders, fills in those relocations. These relocations are similar to the dynamic relocations we looked at before, except these ones are emitted by the compiler and processed by the linker. Again, there's a number of different types, a lot more than I show here. So we have relative relocations. This is where we have a symbol. Suppose we've got an executable and we've got a symbol X, and we've got a reference to symbol X also in the executable. A relative relocation will subtract one address from the other. And this is useful because if our binary is position independent, as the binary moves to different locations in memory, that relative offset doesn't change, which means this relative relocations are quite friendly to position independent binaries. But sometimes we need absolute addresses. We might have, say, a vtable, which needs absolute addresses. And so in that case, when the linker encounters that, if we're building a position-independent executable, the linker will need to convert that relocation into a dynamic relocation. So it will need to be processed at runtime. There's also a whole bunch of TLS-related relocations, such as the offset of a variable within the TLS segment. So the linker's job is to take multiple object files and possibly some shared objects and merge them together into an executable or a shared object. When it does this, it groups sections together according to some rules. So all of the executable sections will be grouped together. All of the read-only sections will be grouped together. All the writable sections will be grouped together. And the same thing for other sections like thread local storage and there's other sections that are related to initialization of a program startup. The compiler can also put alignment on sections, and the linker needs to take this into account. So a section might say that it needs to start at an address that's a multiple of 16, and the link is responsible for making sure that that happens by inserting padding if necessary. So the linker is what decides the layout. It decides where all the different sections get placed and how it can pack them all in an optimal way, and fixing up all the references to the different sections. Linkers can also apply some optimizations. So this is not the same as LTO. These are sort of micro-optimizations. So they're things where the linker has information that the compiler didn't have. For example, suppose the compiler is compiling some code that accesses a thread local variable, and it doesn't know whether that thread local variable will be defined in the same shared object as the reference to it. And so it might pessimistically emit code that uses a very slow method of access that requires a function call. But come link time, the linker might discover that both the thread local variable and the reference are both in the same executable, in which case the linker can use a much more efficient mechanism that only requires 1 or 2 instructions. But that means the linker needs to go and change the machine code that the compiler emitted. And this is often called relaxation in linkers. So LTO is link time optimization. These are optimizations, sort of broader scale optimizations, that are applied after the code has been compiled. There's a few different options in Rust. You can have LTO being turned off, and this is the default for non-optimized builds. You can use thin LTO, which is within the codegen units of one crate. So each crate is split into multiple codegen units, and if we want to have the compiler do optimizations across those codegen units, that's where thin LTO is useful. And this is the default for optimized builds. So if you do -- release. If we want to go further than that, we can use fat LTO, which is across all of the Rust crates that we're building. So this happens just before the Rust compiler calls the C compiler to call the linker, but it's just in Rust code. And it does incur quite a cost, so it will slow down your builds quite a lot, but it might give you a little bit of extra speed in some circumstances. Lastly, we have linker plugin LTO, which, as the name suggests, is where the compiler passes a linker, where the compiler passes a plugin to the linker loads that plugin and gives the plugin the opportunity to perform optimizations across all object files that are being passed to the link. So this means object files that came from the Rust compiler and object files that came from the C compiler. For this to work, you need to have compiled the Rust code and the C code with the same version of LLVM. But if you've done that, then the linker plugin, which in itself embeds LLVM, can pick up those object files and embedded data in them and perform additional optimizations. And this allows you to have things like cross-language inlining, which can be useful for large code bases that are performance sensitive. Things like Firefox use it. So incremental compilation is about speeding up Rust builds when you've already done a build of your crate and now you've made a small change and you want to build it again. So this is mostly when you're doing development work. The idea is, even if you don't have incremental compilation, the cargo will still make a lot of reuse of previous compilations, so it won't rebuild all of your dependencies. However, incremental compilation here in the Rust compiler is going beyond that, and it's reusing compilation from a previous compilation of that crate. So the idea would be when your crate gets built, it will get split up into multiple codegen units, and often there'll be 1 or 2 codegen units per crate. And if you've only made a small change to one module, then often that change will be localized to one of those codegen units, and so the Rust compiler can just redo codegen for that one codegen unit. It also goes beyond that and caches a whole bunch of compiler internals. So there's a lot more work that can be done here. So there's still a lot of work that gets repeated. For example, macro expansion happens every time you build, even if you haven't changed either the macro or the code that it's processing. So this can be expensive for some proc macros, but already it's a lot better than just running without incremental compilation. And Alejandra, who gave a talk yesterday, is doing a bunch of work in this space. So I'm very excited to see what that produces. There's some useful tools you can use if you want to understand more about the structure of the binaries that you're building, such as readelf and objdump, which both show different internal structures within the executable or the object files that you're passing into the link. There's also binsider, which is another tool that I haven't used particularly myself, but I'm told it's a CLI. What do you call it? It's a TUI tool. It's a TUI tool. So if you want something interactive, check out binsider, which Orhan made. So if you want to speed up your builds, one of the good uses of understanding what's going on is speeding up your builds. So a few tips for speeding up builds. The first is to actually measure. So don't just rely on running your build and saying, yes, it felt a bit faster. Actually measure it. If nothing else, look at the time that it prints at the end of cargo build. And perhaps also close your IDE, because if your IDE is open, that could mess with the build times. Removing unnecessary dependencies. So if you've got some dependencies that are large and take a long time to compile, and maybe you're not using all of them. Maybe they have some features you can turn off in order to cut down their build times. One good way to figure out where you can cut costs is by running cargo build -- timings, which generates a HTML page that has a whole bunch of useful content, including something that looks like this. So this Gantt chart here shows when it started and finished building each of the crates in your dependency tree. So the purple part is where the compiler is doing code gen, and the blue part is everything before that the Rust compiler runs. So importantly here, the blue part, once it finishes the blue part, the compiler is then free to, or the cargo is free to build crates that depend on your crate. So it's called pipelined execution, and it means that it can do more work in parallel earlier on. The orange parts are build scripts. So in this case, we've got a couple of long-running build scripts that are most likely building C code. And so if that's on your critical path, maybe there's a Rust native version of the library you can use instead of the C version, and that might speed up your builds. Another useful thing that's on the same page is this graph of CPU usage. So we can see here the dark orange in the background is a graph of CPU usage. We can see that for the first 2/3 of the build, it's fairly high. It's close to 100%. And then for the last part of the build, it drops down quite a bit with a few spikes. And that's because we've finished most of the parallel operations, and we've only got maybe 1 or 2 crates left to build. So there's just not enough work to keep all of the cores active. Another useful flag that's only available on Lightly is -z time passes. So this prints how long the compiler spends in different phases of the compiler. So some of these phases might not make sense if you don't know about compiler internals, but a lot of them you can probably guess what they're doing. So the way I would use this is if I want to speed up my incremental compilation, I would run this once and then make a small change to my code and run it again. And I would look to see if there was one particular phase that stands out as taking a long, long time. And suppose it's something like macro expansion, then I would look and see if I've got some very expensive macros that I'm using. And maybe I can cut that macro usage a bit, or maybe I can turn on optimizations for those macros so that they can run more efficiently if they're very expensive computationally. Alternatively, if I see that linking is taking a long time, you should switch to a faster linker if possible. So there's several fast linkers available for Linux. The good news is that LLD is going to be made the default from 1.90, so even if you do nothing, you'll get a faster linker there. Or you could also check out Mold or the linker I've been writing, Wild. But benchmark them and see how they go on your machine with your program. LLVM lines is a cargo plugin that lets you see how much LLVM bitcode is generated for different lines of your code. So this is a good way to see if some part of your program is, so suppose you've got a generic function that is being expanded lots by some macros. That might be causing a lot of work for LLVM. This is a good way to see where you've got some hot code that you might be able to do that less, to make it a bit easier for LLVM to optimize your code. Another bit of advice that often gets given is splitting your crate into multiple crates. And I can see where this advice is coming from. It comes from the idea that the unit of compilation is a crate. And while that's true, incremental compilation means that it's not really what affects your build times. And the issue with splitting a crate out, if you split some of your code out into a separate crate, if you're making lots of changes to that code that you split out, then every time you make a change, it's got to rebuild that crate And if you're building the workspace, it has to rebuild all the crates that depend on it. And so you can often end up actually slowing down your builds if you split out stuff into a separate crate, depending on circumstances. So just be a bit careful with doing that. I tend not to split crates for that reason. I'll split for other reasons. Lastly, if you don't use a debugger, if you don't need debug info much, then I would suggest turning it off because it is quite expensive to build with debug info. So I usually have a separate profile that I use with debug info only when I need it. And my default builds don't have debug info. So thank you all for listening to the talk, and thank you to the organizers for giving me the opportunity to come here, and also thank you to my generous GitHub sponsors, for some of whom are listed here, for giving me the opportunity to work on this kind of stuff full time. Thanks.